All right, cool. Second part, find the total work done. I really like this problem because it makes you go through multiple methods. So this first thing that we just did here, all of this was not work energy. All of this was free body diagram was called acceleration. I call it acceleration analysis. All right. So I just
Mm-hmm.
put free body diagram. That's all the part A was. Part B is completely different. Part B is actually going to be work energy because they
Yeah,
said
which is
it.
like,
They said it. They specifically targeted work, which is fine. You're going to have problems that do that. It's not really a big deal. It just means you need to know how to work with free body diagram versus work energy, and when you're gonna pick and choose. Because later on, they're not gonna say, "Oh yeah, use this method." They're gonna just say, "Give me the answer," and you have to know because of what they gave me, I'm gonna do a free body diagram, or because of what they gave me, I'm gonna do work energy, or because of what they gave me, I'm gonna do impulse momentum. And later on, when we get to that type of problem, I'll show you how to know which one for what. Okay.
mm-hmm.
Everything in this class breaks down very simply. Everything in this class breaks down simply except 3D inertia. That's the only thing that's hard in this class. Everything else is easy. So find the total work done by all the forces acting on the crate. All right, so we have, let's put it in, I don't know, blue, whatever. So we want to go each force. So we got this guy, this guy, this guy, this guy, this guy. So that's 5 forces. You see that?
Mm-hmm.
So each of those forces is going to have a work associated with them. All right, that's not a big deal. So do you know the definition of work, the mathematical definition of work, like the formula for it?
Isn't it the summation of this summation of work done on an object is like T2 minus T1, I think, and then T is equal to mv squared over 2.
Yes, you're right. What you said is right, but that's not what I'm looking for. What you said, this right here is spot on. What you basically
Mm-hmm.
said was that work equals the change in kinetic energy. Now, that's a partial statement.
Oh,
There's
but then the velocity is
yeah,
like the
there's some
change
other
in
stuff.
velocity,
No, no, no.
I
What you
think.
said is right. It's just that there's some
Okay.
other stuff to add on to it, but we're not there yet. Okay. Now, what you said is not wrong, but that's not what I'm looking for. All right.
Mm-hmm.
What do I mean by that? You said that the sum of all work was the kinetic energy change. I put KE because it's easier. You define kinetic energy. There's a definition for work. Okay.
Mm-hmm.
Work is defined as, and I'm going to put it in both ways. I'm going to put it in the calculus way because I know your professor likes to give calculus. And I'm going to put it in the non-calculus way. So the calculus way first, work is defined as the integral of force dot ds. That's the technical definition of the term work. So that's what this guy is. Okay.
Mm-hmm.
So I'm going to erase this bottom part, which we can come back to later. It's whatever. And that's that. So this will be useful. Note this dot product basically says the same direction parts, the parts in the same direction. In same direction. So what this means is if your object, let's look at our block actually. If your object is being pushed with a force like that, right? We know that it has an X part and it has a Y part. They have to tell you the direction that the work is going to be considered in. That's actually really important because what happens is on the ground, we know that it's only going to slide my S. You see what I'm saying? It's going to slide that distance S.
Yeah.
So the only thing that can actually produce work is the X part because the X is in the same direction as my S. You follow me?
Mm-hmm.
And so in this case, it actually breaks down into work energy devolves or simplifies into F delta S, where F has to be in the direction of S. You follow me? So a lot of time what people will do is they'll say, oh, there's an angle here, some theta. So what they'll do is they'll rewrite it like this. They'll say F cosine of theta times S. Okay?
Mm-hmm.
And so what that does is it automatically produces that guy, which is the X value. Okay. Now, obviously, if your delta S were not sideways, but it were downward, then what you'd actually be
It'll be
working with,
sine.
no, not sine, it would be this guy that does work because that's the guy that points downward. You follow me?
Yeah.
So what happens is this is what all students mess up. It turns out, let me see if I can.
Or would you add mg?
You would, but I'm not considering mg right now. I'm just considering that
Okay.
force. Just considering that force. Each force does its own amount of work, and at the end they all add up. Now, what this means, though, very, very important. This guy right here does no work in that direction because he's perpendicular. If you are not moving in the direction of the force, then that force is not actually doing work. Does that make some sense?
Yeah.
That's really confusing for a lot of students. So by the caveat, this guy is doing no work when it comes down to moving sideways. So for sideways motion, downward forces do nothing. You're wasting energy. You're not doing anything. You're turning that energy directly into heat. Heat is not work. Okay? And you'll learn more about that when you get to thermodynamics. But for now, that's all you got to understand is that if the force direction is perpendicular to the direction of the motion, that force does no work. And we're going to use that right now to solve. Okay?
Mm-hmm.
All right. So I'm actually going to move that to the side because that was pretty important for you to know. And that gets a lot of students. But what we're actually going to do is we're going to look at the situation. So let's pull our vision back up here and we'll get to work. So we'll do each force. We'll say the 500 force. So we'll say the work of the 500. Mind you, we know that the motion of this bad boy is going to be to the left, right? That's going to be my delta S direction. You follow me?
Mm-hmm.
They said that the distance was 5 meters. You see that?
Mm-hmm.
And so now we know what our S is. It's 5. So everything that we put here is going to be times by 5, as long as it's in the right direction. So I'm just going to draw it each time because it's going to make it a little bit easier for me. That's my 500. And I know that this is my distance. So my question is, am I going to do 500 times 5? Is that the right way to put it?
No.
No. Why is it not that?
Because it's in a 45 degree, the direction is the force being applied is in a 45 degree angle.
Perfect. And there's nothing else you have to say. You got to take the X value of that, which is going to be 500 cosine of the 45 degrees, then times 5. You follow me?
Mm-hmm.
Easy work. So 500 cosine of 45, I put a tangent by mistake, times 5, that's going to be 1768. So 1768, Jesus Christ, what's the unit for joules? Joules is going to be of work is going to be done by the 500. You with me?
Yep.
Now, here's my question. If I were to look at the upward component of the 500, how much work does that do?
The upward component of the 500? I mean, 0 in this case?
Yes, my man, you got it. You completely understand. That guy does 0. Cool?
Mm-hmm.
So now you get that. I'm only going to do 2 more because I understand that you understand that you just do this 5 more times. So now let's look at the work of the weight. Looking at the weight exclusively, we know that the weight exclusively points down, and that's my direction of motion. So what's the work of my weight?
Well, there's no angle to it, so wouldn't it just be mass times gravity times 5?
Are you sure? Mass times gravity times 5. But look at the direction of the force.
It's the direction of force is so would it be 0? Oh, it would be.
Yep, it would be 0 because the cosine of 90 is equal to 0. So if ever you're in doubt, just put the cosine term on, and the cosine term will literally solve it for you.
Oh wow!
See how that works? Math, the math that we build, you get 0 joules of work. The math that we build has to always make sense in real life. So even if you mess up, if you know how to use the equation, if you're really, really good in math, you don't really have to know all of the engineering. I am somebody who learns the engineering first and the math second. I've always been that way. So I always teach the engineering first and then use the math to prove what I'm talking about later. But just so you can see it, that right there was the proof that we needed. Cool? Mm-hmm. Last but not least, I'm going to do the friction. So the friction value, the work of the friction, just draw it up here. And this one's going to be interesting because we know that it moves this way, right?
Mm-hmm.
But the friction points that way. So what does that mean for my work value?
It's negative.
Yes, and there is a such thing as negative work. Negative work means that energy is being taken away. So negative work is draining the energy, which friction always does. Friction's always going to do negative work. Positive work
just slowing
is,
it down.
yep, positive work is adding energy. Friction always does negative work because it's always slowing your object down. And so this one's just going to be 0.2 times 320, which is friction. I got to put a negative on that bad boy because it's negative, and then I do times by my 5 meters. Am I good with just doing 320 times 0.2 times 5, or do I need a cosine?
You don't need a cosine because it's perpendicular. I mean, so isn't it parallel to the surface? So I don't think you don't need a cosine.
Yeah, no, you got it. That's exactly right. You do not need the cosine because it's parallel to the actual direction. You're good. That's going to be negative 320 joules of work, and that's how you do your works. And you just do the other two to find
Where'd
that.
you get the? I thought it was 0.2 times 5 or something.
Yeah, 0.2 times 5 is 1.
Oh, okay, yeah.
Yeah, so it nullified. That was convenient. That's just a convenient situation.
Okay.
Cool. So that's how you would do these. Obviously, there are 2 more, but this is the meat behind what needs to be done for this problem. So that we're going to chalk it up to being done. Any questions?
So far, no, but I'm assuming you use the normal force that you had already found earlier.
Yeah, I used what we solved for. Once you solve for something, that thing counts as a value. So I just use the 0.2 times 320. That's where that goes.
Yeah. Okay.
Dope. So that's part B. It's done. So mind you, part A and part B are 2 different types of problems, right?
Yeah.
The thing is, though, note something. Note that you needed to find the normal force to even do part B. And so that's what a lot of students are going to get tripped up with. She's literally walking you through this problem. She's being nice. I'm not going to lie to you. Because if I was your teacher, I wouldn't say that. I wouldn't say find the friction. I would say find the work done. And you'd have to figure it out on your own. And
this is somebody's old test. Mm-hmm.
Yeah, and as a student, you have to understand, you would literally be working on this, and then you'd say, oh, crap, I don't know what friction is. And you say, what's my friction? And then you say, oh, God, I got to go do a free body diagram to figure that out. You always do. Typically, you do a free body diagram to figure out friction. You see what I'm saying?
Mm-hmm. Yeah.
So that's the type of thinking that you'd have to go through, like more traditionally. Like if she didn't want to be, like if she because she's really being nice about it. Like if she didn't want to be nice, she could have just said, figure out the work. And you'd have to go and do the free body diagram on your own. So that's how that works. Cool?
Yeah.
All right, last but not least, it says find the velocity of the crate at that instant. All right, cool. So what we're gonna do is I'm gonna just I actually need to find the work of this vector right here because I'm gonna do another work energy equation. So what I've done here, this is not work energy. This is not work energy. It's not. It's a part of work energy. Okay.
Mm-hmm.
So what we're going to do is now I'm going to teach you the work energy equation. And once I've taught you the work energy equation, I'm going to solve this at my speed, and then you'll be able to follow me a little bit better. Make some sense?
Yeah.
All right. So part 3 is still work energy. Part C, it's still work energy, but it's the actual work energy, not just work. Because if you notice, everything that we focused on here was just figuring out what the work was. Work energy is now what you were talking about, and I'm going to detail it now. Okay. So the work energy equation is as you said, but I'm going to give you the full rendition because that's how I get down. I'm not going to do it like how your professor writes it. I'm going to write it my way. You with me?
Mm-hmm.
So first I'm going to put it in a generic form so that you can understand it. And then I'm going to put the equation. The work energy equation is very, very simple. It says this. Everything in the universe has an energetic composition. We're going to call that what this is, energy 1. The energy 1 of a situation. So the energy can always be measured. It takes a lot of science, but energy can always be measured for anything. If I take the computer sitting in front of me, that computer has a certain amount of energy stored in different forms. So energy can be everything that's associated with reality has an energy associated with it. So the fact that the computer is hot, there's an energy associated with that heat. The fact that the computer has electricity inside of it, there's energy associated with that. So that'd be the energy of the electricity plus the energy of the heat. You see what I'm saying? Plus the fact that the computer is literally I'm sitting on the third floor. The third floor away from Earth, there's an energy associated with its position. So I'm going to call it the energy of the position, which is actually gravitational energy. You follow me?
Yeah.
Plus the energy stored in the mass of the computer. Everything, all of these bad boys, there's tons of energy values associated with it. When you add them all up, we get the energetic composition of the computer right now. You see what I'm saying?
Yeah, that's kind of why circuits and dynamics is kind of similar, but like different.
Yes, all engineering is kind of similar but different. And I'm going to tell you what, thermodynamics is the one thing. Thermodynamics and feedback, those are the two classes that connect all the engineerings. All of them have feedback and thermodynamics, all of them. And so those are going to be the parts that actually seem the most familiar. Everything else is just like they kind of branch off from there. All right. Now, what I'm going to do is I'm going to erase this because I don't actually want you to focus on all those different energies. I'm going to tell you in a second what energies we focus on. But the point is, if I want to move my computer, if I want to do something to my computer, whenever you do something to something, you're doing work. That's just how it works. Whenever something is done to something else, work or energy, energy has to be changed. And that's just the way it is. So think of energy. Think of energy flow as the reason behind change. So they always say work is the capacity to do energy or whatever it is. Energy is the capacity to do work. Work is energy in motion. That's the best way of saying it. Work is energy in motion. And it turns out that there's another way of doing energy in motion, and that's heat. Heat is also energy in motion. And that's all that there is. There's work and there's heat, and that's it. That's all that there is in the universe is work and heat. Okay?
Okay.
Now, in dynamics, you don't focus on heat, obviously. In thermodynamics, you focus on heat, but work is energy in motion. So the whole idea is I start with some format, then I do something. You see what I'm saying?
Mm-hmm.
And then obviously, I'm going to end in a new situation. You follow me?
Yep.
It's very, very simple. I start with one energy. I do something to my situation, and I'm going to have a new energy associated with it. Period. That's just got to be how it works. Make some sense?
Yep.
And that's that. That's how the work. That's the core. That's the fundamental idea behind work energy. Now I just got to show you how it looks like in an actual equation, because this equation doesn't give you the terms that you need. Cool.
Yep.
I literally teach students this first and foremost. I don't teach them how to do work and then how to forget that. That's stupid. You teach them the equation first, and then you teach them the terms. So what I'm doing with you is I'm literally just shortcut teaching you how I do it. So now all you got to do is you got to know that energy one is made up of God, I always forget how many pieces. I'm just going to write them out. Energy one is made of 3 pieces in this class. In real life, it's made of tons of pieces, but for this class, we're only going to focus on 3 pieces right now. First, it's going to be the kinetic energy. Mm-hmm. Kinetic energy is defined as 1/2 mv squared, which you already said.
Yeah.
Plus, and what people do is they say potential energy. So kinetic energy plus potential energy. But the thing is, potential energy is actually broken down into 2 terms. So the first term is going to be the gravitational potential. That's going to be the energy associated with the height. So this guy right here is the speed energy. This is the height energy. And then there's going to be another energy that we're going to need for the next problem, which is the the spring energy. And that's going to be 1/2 k delta x, and that quantity squared. Mm-hmm. And this is the spring energy. So let's not call it spring energy. Let's call it compression energy. Because you know that when you're squeezing a spring, it pushes back. That pushing back is the energy of compression. It's a compression energy.
Yeah.
Okay? That's literally it. Everything you need to know is I've already taught you about work energy. Everything from here is just you seeing how it works in action. Okay? Mm-hmm. All right. So I'm going to leave it like that. And so what we're going to do is we're going to write it like this. I love to write the equation like this because that's my shortcut. But when you're really writing it, you have to write everything out. So you're going to put 1/2 mv1 squared plus mgh1, because that represents the first situation, plus 1/2 k delta x1 squared, plus any work. But now remember, you know work is going to be force times distance. Sum of all forces times distance, right? Mm-hmm. So that's going to be your free body diagram part. So that's where your free body diagram comes in. Equals, and I do everything but for the second situation, 1/2 mv2 squared plus mgh2 plus 1/2 k delta x2 squared. This monster of an equation is the
Applies to
full
everything.
work energy equation, and you will just use this and use this and use this. Are you with me?
Yep.
Now, it looks really, really intimidating when I write it fully like that. That's why I don't like to write it all out. Because in
Wait, no,
thermodynamics,
actually, I don't know. That kind of makes sense though, because
yeah, of
then, like,
course.
I get why like T2 minus T1 is a thing, because it's just the energy and work done at
It's
a
those
certain
two.
instance minus
Yep.
the two initials. But
Yep.
then because it's like only moving like perpendicular to it, you get like MGH, was the potential energy, that would be zero, and then there's no
Yep.
spring either, so that would be
Yep.
zero. And that's how
Exactly.
I can set that equal to zero and solve for it.
Yes, exactly. And so you already understand how to work it. This equation is the life spring from all of the renditions that you're going to run into. And so literally what you just said about how the gravity goes away or how the spring goes away, that's all you're going to be doing. This is my equation. Gravity goes away, so that's going to be zero. Spring goes away, so that's zero. Easy peasy. Okay. And so that's actually what happens here. That is what happens here. What I'm going to do is I'm going to show you my full way though, because I don't want you to. Here's the thing. I never write all of that out. I never write that first. I'm not going to lie. I just wrote that for you because I want you to see the equation.
Yeah, you want me to understand the concept.
Yeah.
That makes sense.
But I never do that. What I do is this. I put a box. And I break the box into two. And then I break those two boxes into four. And I literally, I don't know why, but for some reason, students love this. I don't know why they love it. This is what I do for myself. This box right here is my shortcut. This is how I do all the work energy. I just fill in this box and I go. All right. So this is what I do. I put my box. On the left is my situation 1. On the right is my situation 2. The top part of the box is the work, because technically to change from 1 to 2 is going to require both of them. Technically, it's the work done from 1 to 2. And so that box takes up both of them. Does that make some sense?
Yes.
That's going to be the conversion. So we know, oh, actually, I'm jumping the gun. Then under that, I put kinetic energy. Then I put gravity. And then I put spring. And so I'll break it down like this. A lot of times students, when they try to remember all of this, they forget. I don't know why. They just forget terms. So what I do is I put this box, and when I put this box, they never forget the terms because I don't know. It just works like that. Okay. All right. All you got to do is fill this in. Literally, that's your job. Your job is to fill this in. Fill it in. And when you fill it in, you're building this equation. That's all you're doing. All right. So we know we're going to take the works that we figured out. So we know we got 1768. And we literally plug and chug. Literally, you just go, okay. The works that we know are already found. So we got 1768 plus or minus 320. And then we're going to go plus. We need another work. I need the work done from the 200 force that I never did.
Mm-hmm.
I know the 200 force is pointing down. That's going to be 200 cosine of 30, and that's times by 5, which would be 1,000 times the cosine of 30, which is 866. So I put plus 866. You following me?
Mm-hmm.
The work of the normal force is equal to 0 because of all the stuff that I was saying before. So bam, all of my works, I literally just put all of them in that one box. You see how I did that?
Mm-hmm.
All right, great. And that's generally what you're going to have to do. If you do not already know this stuff right here, you're going to need to use your free body diagram to figure it out. That's just how it works. The work box is generally done with a free body diagram or an integral, okay?
Mm-hmm.
All right, cool. From here, it's easy. Once you fill that in, literally, this right here is the hardest part. Once you fill that part in, everything else is cake. So the kinetic energy, 1/2 mv squared. But what was the V1? 0. I told you, it starts from rest. On the second side, if you don't know what it is, write the variables. So put 1/2 V2 squared. I don't know what it is. That's what I'm solving for, actually. They want the speed. That's what I want. So I'm going to put a little double underline right here. Okay, that's what I want. So that's that. The second part, gravity. 1/2, I'm sorry, MGH. MGH1. Now here's the thing. Generally speaking,
There's no height in here.
Exactly. There is no height.
So 0.
Exactly. More specifically, there's no change in height in here. Because what happens is you're only going to have potential when an object has a vertical displacement. If there's a vertical displacement, then that's going to be where the gravity goes. But because there's no vertical displacement, we can just say that there's no height. You with me?
Mm-hmm.
All right, awesome. And so what we end up with having is 2 zeros. A lot of time you'll just see me do this. I'll just slash them out. And this has no springs in it, so I'm just say that there are no springs. You follow me?
Yep.
And so, last but not least, now that I put my box together, I don't know why students love this. I don't know why it works for them. Once you fill it in, you just do 1 plus the work equals the 2's. Literally. So you add up all the 1s. So you literally take all of this side plus the work box, and then you add up all of those, and that's all you have to do. You with me?
Mm-hmm.
Actually, let me actually I like the way that looks, so I'm going to put a little arrow here, a plus, and then another arrow. And so what that looks like is 0 on the left plus 1768 minus 320 plus 866 equals, and the only thing on the right is 1/2 mv squared, and we know that the m is 50. And so this is how you get work is all of this stuff equals T2 minus T1. It's just that T1 is 0. So you get the work equals 2. So all of what you said before, this is the proof behind it and then some, because this is never going to steer you wrong. With what I just showed you, you're never going to get work energy problems wrong unless you mess up a negative, which is very difficult to do.
Okay.
All right. Work energy is honestly the easiest thing in dynamics if you do this method the way I just showed you. Like, I've never had a student had issues with work energy because it's so straightforward. Of course, there are little things about it that are difficult, but it's basically straightforward. One little tip, you can only have one unknown. Only one unknown. So
Yeah, because it creates one equation. That makes sense.
Exactly. And later on, we're going to learn another work energy where you're going to have 2 unknowns, but that's not important right now. For now, you just got your one unknown. All you got to do is solve for your velocity. Velocity is going to be the square root of, it's 2 times 1768 minus 320 plus 866, all quantity divided by 50. All right, so let me figure that out real quick. 1768 minus 320 plus 866 times 2 divided by 50. That's 92.56. And that'll be meters per second. And that is your answer. And that's it. That's all you had to do.
Okay.
You following me?
Yep.
Easy peasy, right?